Okay, so we're looking now at how we can differentiate functions which are known as implicit functions. And these are ones such that we can't rearrange them to get y in terms of x or x in terms of y. It's just not possible to do that. So the method that we're going to develop here is just an extension again of the good old chain rule. So let's take a look at this equation here of a circle. So we've got x squared plus y squared plus 4x minus 6y equals 12. So if I want a gradient function, I want dy dx. So I need to differentiate every term here with respect to x. So I'm going to do d dx of x squared. Then I need to differentiate the y squared with respect to x, 4x with respect to x, and the 6y, and the constant, like that. So as I say, differentiating functions of x with respect to x is straightforward. If you just differentiate x squared with respect to x, you get 2x. The problem comes when trying to differentiate a function of y with respect to x. And this is where we're going to use the chain rule. So if I had a function z is y squared, then if I differentiated z with respect to y, I get dz dy, which would be 2y. But if we want dz dx, then using the chain rule, if you think back to how I've been sort of writing this on occasions, if I want dz dx, and I want to introduce a third variable, then that would be dz d something times the d something, the third variable, dx. And then whatever that third variable is will cancel. So in this case, the third variable is y. So where in this case the cloud is y. So dz dx would be dz dy times dy dx. So what we're doing is, if I want to differentiate y squared with respect to x, what I end up doing, because the dz dy is differentiating that with respect to y, and then multiplying it by dy dx. So the differential, if I'm differentiating y squared with respect to x, what I'm going to end up with is 2y, what I get by differentiating that, multiplied by dy dx. Okay? Which I've then generalized over the page. So to differentiate a function of y with respect to x, we differentiate with respect to y and then multiply it by dy dx. So d dx of a function of y is d dy of the function of y times dy dx. So going back to our circle, what that means is I can now differentiate each part of this with respect to x. And I'm going to get 2x plus, that is now going to be 2y dy dx. That's going to be plus 4. And that's going to be minus, differentiated with respect to y, and you get 6. And then multiply that by dy dx. And that's equal to 0. Okie doke. So what I want to do now is to get my dy's together. Basically this is like a GCSE higher tier rearranging formally now. I want to get the y's on their own. So the dy dx is on their own. Now because those are all positive where they are, so if you think that what I'm going to do is leave the 2x and the 4 where they are, and bring the dy dx's onto the right hand side, I get that. I can divide throughout by 2 to give me x plus 2 equals, and I'm going to take the dy dx out as a common factor here. So I've divided by 2 to get 3 minus y, which gives me that, and that then will lead to get the dy dx on its own, I'm going to divide by 3 minus y, so I'll end up with dy dx equals x plus 2 over 3 minus y. So the gradient function of the equation of the circle that we were given is going to be found by substituting in at any given point we would need to know the corresponding x and y coordinates, and then we would get the gradient function out of that. If they want to make these harder, the sort of questions with the implicit differentiation, and if we go back to our folium of Descartes at the start, then it becomes a little bit more complicated because they can stick in a product rule, and that's what the next example is going to look at.